In my role now, I'm responsible for the product strategy for quantum computing at NVIDIA. Um, AI is increasingly becoming a part of that strategy as it's becoming, a really important part of all science. And given the topics of the conference, I thought it'd be really important and interesting to talk about the intersection of AI and quantum computing, how we see it, what lessons we can learn. Um, yeah, so this is a rough agenda. This isn't really in order, but these are the questions that I'm going to try to address. Where is AI and AI supercomputing today? Where is quantum computing today? Most importantly, how can AI and quantum computing work together? And in particular, what can we do with AI and what can we learn from AI to help enable the future of quantum computing that we all want and we're all excited about? And then finally, how NVIDIA sees it and what we're doing in the space. All right, and so I'll start with kind of a little bit of history. So I think to understand, where we are in quantum computing today, where we want to go, and how NVIDIA is thinking about it, it's good to look at kind of some past revolutions in computing and revolutions in accelerated computing. So going back about 25 years ago, NVIDIA invented this technology called the GPU, the graphics processing unit. And so in contrast to the CPU, which is a general purpose computer and processes things, operations one at a time, a GPU is optimized to process many operations at once. And the first application of this was graphics. So video games and other applications for graphics, where you want to do many of the same operation. There's the same operation many times. It turned out that there are, and it turns out today that there have been many more applications for accelerated computing and for using this model of computing. And shortly after the invention of the GPU, there were some very clever researchers who started using it to solve scientific computing problems. And this was exciting. It was also quite painful. It consisted of kind of hacking these tools called programmable shaders to make them solve the matrix math problem that you wanted instead of display graphics. And so it was unnecessarily slow. And then about 20 years ago, NVIDIA released a technology called CUDA. And so CUDA stands for Compute Unified Device Architecture. I won't go too deep into what it is, but basically what it meant is if you could program in C, you could program a GPU. And so this really democratized accelerated computing and opened it up to a broad set of researchers and developers. And the effect of this was transformative. Before CUDA, almost no supercomputers had GPUs in them. Actually, none did. Now, almost all of them have GPUs at their heart, and GPUs are used for solving a very large set of the important computational and scientific problems today. Fast forward a little bit to deep learning. So in 2012, there was kind of a big bang moment for deep learning when a group of researchers at the University of Toronto discovered that you could use a GPU to train a convolutional neural network and get results much better than had been seen before. So on a deep learning challenge, they set a world record for performance using a single GPU. And this was, as I said, sort of a big bang moment about 12 years ago that led to the explosion of deep learning we see today. And this is around the time NVIDIA started investing heavily in deep learning. Fast forward a few more years, and there were a couple of big developments in generative AI. Most importantly, the transformer paper from the research team at Google in 2017 that sparked the revolution in large language models. NVIDIA started investing around the same time, actually a little bit before. This picture is maybe too small to see well, but it's from 2016 of our CEO, Jensen Huang, hand delivering one of the very first systems called DGX that we make to then a very new, very unknown startup called OpenAI. And of course, now we're all familiar with ChatGPT and what's come out of OpenAI and companies like it. But NVIDIA started investing well ahead of time. And so now we're all kind of thinking about when quantum computing is going to make a big impact and what's needed to do that. Most people on this call probably know that quantum computing is not useful today, but the long-term potential is very exciting. And the way that we see it is, just like we did for all these other technologies, it's really important for a company like NVIDIA, with perspective on accelerated computing revolutions, to start investing today, build the tools and the platforms needed to enable these breakthroughs, the quantum equivalent of ChatGPT, and work with every researcher and group that we can to solve their problems and help them succeed. So that's really how we're thinking about it. And so with that, I'm going to zoom in a little bit on AI and generative AI for a minute. And so this chart on the right represents in an interpretive way performance of compute over time. And so computing has been fueling scientific discovery, powering industrial automation for decades. And for a while, that meant CPU performance improving year after year, known as Moore's law. And that's the blue line here. And you'll see, in the last decade, that's really leveled off. So Moore's law has ended. We've sort of squeezed everything out of CPUs that we can. But there have been a set of new computing revolutions that have kind of continued to push computing power forward and enabled more powerful computing to solve more larger and significant scientific problems. And so that's accelerated computing with the GPU, the scaling up and out of these systems. So building, rather than single GPU, full GPU supercomputers, which I'll talk about a little bit later. And then most recently, machine learning, AI, artificial intelligence. And so generative AI is the key technology that's starting to enable the breakthrough science we see today. And this takes many forms. I'm a quantum physicist, less than a chemist or a biologist, and so I won't get into details on all of these. But for one example, with weather forecasting, for decades, people have used these numerical weather prediction models that are just kind of fundamentally limited. So the best resolution today is about 10 kilometers, which is useful for some things, but not useful for a lot of what we want to do, like predicting extreme weather events. And the scaling is really bad. So to get 10 times better resolution than that, to get down to 1 kilometer, we'd need about 10,000 times more compute without AI. Weather is also kind of famously unpredictable and chaotic. We need lots and lots of ensembles of data to predict with high probability the weather and especially extreme events. And the set of solutions that are evolving to tackle this challenge are actually data-driven transformer models and generative AI models, diffusion models. They found to be about 1,000 times faster than the old numerical weather prediction models, actually with better accuracy and the ability to predict extreme events. And so NVIDIA has been demonstrating this first in Taiwan, which is a small country, and now scaling it up with a digital twin of the Earth called Earth 2. So that's one example. The same kind of thinking applies to a broad range of scientific fields like astronomy, chemistry, protein discovery. I know there are speakers elsewhere in this program who are tackling those with more detail. So I won't get into it, but the common theme here is generative AI is offering a big leap forward in how we can think about and tackle these problems. And so, how is NVIDIA building the platform for this? So um, it's available at a few different levels. So starting with the very top, we do build kind of a full set of software and solutions for all of these domain-specific problems. So everything from CAD and simulation design automation to simulation of climate that I talked about, quantum computing, which I will talk about, robotics and industrial digital twins. So domain-specific software. All of this rests on fundamental libraries to get the most performance out of CUDA for a particular application. And all of that rests on the accelerated computing hardware and systems that NVIDIA builds. So not just the GPU, also the CPU and the data processing unit or DPU and the systems that you can construct out of them. And critically, this is an open platform. So you do not have to plug in at the top level. Most people do that. If you're building your own software, you can take the CUDA-X libraries directly and use them. If you're building your own hardware systems, you can take the hardware that NVIDIA builds and construct your own compute solution. So we build the full stack, and then we go to market in a disaggregated way so that whatever a researcher or a group is doing, they can make use of our technology at the right level for them. And what this enabled is the ability for us to partner very broadly. And this is a really important part of how we think and strategize. And so in AI, we want to be the only AI company to work with every other AI company. And that's been very successful. So this is a representative set of our partners, including those plugging in at the hardware level, so building their own GPU systems, plugging into the software level, so building their own software solutions on top of our libraries, all the way up to the cloud service providers who are offering kind of the full set of NVIDIA technologies. And so we're very proud to support all of this work. And we're also building the world's most powerful systems for research. So this picture is a supercomputer called Jupiter. It's being constructed now at the Jülich Supercomputer Center in Germany, built with a few partners, including Eviden. And this is going to be the most powerful research supercomputer in the world when it's finished. So it will be over an exaflop of HPC performance and 93 exaflops of AI. It's built out of tens of thousands of our Grace Hopper superchip, which I'll talk about, and the full kind of networking and software stack on top of it. So this is going to be an on-premise supercomputer. We're also helping to build supercomputers in the cloud. So this was also recently announced. This is the world's largest supercomputer available over the cloud, built with Microsoft Azure, so that if you have a laptop, you have access to one of the world's most powerful systems. And so this kind of work is really key to enabling everybody to take advantage of the platform that we've built for important scientific discoveries. So with that bit of background, let's move to quantum computing. I know there are also many quantum computing talks in this program, and so I won't give a super deep technical explanation of quantum computing, but suffice to say, it represents a very exciting opportunity to solve important problems in a new way. And there's now a massive global effort to realize the potential of quantum computing. And so this includes national quantum initiatives in dozens of countries, hundreds and hundreds of quantum computing startups. The majority of Fortune 500 companies invested in quantum computing in some way, and tens of thousands of research papers. And so, this is, though we're not yet at useful quantum computing, and it may be a while, clearly an exploding domain of science. And I think it's natural, given all the excitement about quantum computing, to then turn to okay, so what's standing in the way, or what's standing between now and useful quantum computing? Well, there are a few pretty tough challenges. I think most critical is the quality of the qubits, so qubit fidelity. Quantum computers, when they operate, are kind of inherently sensitive to noise, and errors compound during during a calculation. Yeah, sorry for my cough. And so it's important to drive down the error rates as low as possible. We think we need 3 or 4 nines of 2-qubit gate fidelity in order to do useful quantum computing. We also need to scale up from today's systems. So it's estimated that to start to solve useful problems with quantum computers, we need maybe 100,000 to 1,000,000 qubits or more. Today, the biggest systems are maybe a few hundred, so a few orders of magnitude needed there. We need to integrate quantum computers with accelerated computing and HPC. So quantum computers are not general purpose computers. They're good for specific problems and really not good at a lot of other things. And so the consensus is that what useful quantum computing will look like is integrated with CPUs and GPUs, and each type of processor kind of doing what they're good for. We need to learn how to correct the errors. So even with 99.99 2-qubit gate fidelity, if we want to use a quantum computer with millions of clock cycles, we need even better than that. And so we need to do this thing called quantum error correction. And even if we've done all that, the set of algorithms where it's known that quantum computers will have an advantage is really small, or at least an exponential advantage is really small. And so algorithms research to discover how quantum computers are going to help for the types of problems we really care about is critical. And finally, and to enable all of this, we need better access to quantum computing resources. So today, the number of quantum computers in the world is small. They are small and noisy themselves and hard to get access to. To make progress on all of this, we need to enable a broader community to start to make use of quantum computing and do research in quantum computing. And so given the two topics I've talked about, it's natural to ask, how are quantum computing and AI going to work together, or how could they work together? And one question you might ask is, can quantum computing enable better AI? So it's certainly possible. Quantum computers kind of inherently can explore a broader solution space. They can be more expressive in the training phase. And so there's reason to think that they could offer an advantage. But it's important to understand that, first of all, this is really far in the future. And second, there are some good reasons to think this is going to be really challenging. So in AI in general, you want to be able to load very large amounts of data. If there's one thing that we've learned, it's that with small amounts of data, AI is pretty bad. And as you add more and more and more data, eventually magic happens. And for quantum computers, loading data into a quantum computer is a really hard, unsolved problem, at least doing it efficiently. And so that will need to be figured out for quantum computing to really make an impact for AI. And just kind of from first principles, if we think about where quantum computing is likely to have an impact near term, I think it makes sense to look at problems where today's computers are struggling, and AI is sort of the opposite of that. We're seeing progress in AI, the likes of which haven't been seen in any other computing domain, in my opinion. And so it's not a field that's standing still. The bar for quantum computers to provide an advantage is moving further and further away quickly. So not promising near term, but really interesting research, and we are supporting that with our platform. But the second question you might ask is, can AI enable better quantum computing? And I think the answer to this is a resounding yes, and it's already happening. And I'm going to talk about that in the next couple of slides. And given how quickly AI is advancing, we believe we're just scratching the surface of what's possible here. And so, if you take one thing away from this talk, I'd like it to be, when we think about quantum computing and AI, the really exciting opportunity today is AI enabling progress in quantum computing. And to go back to the challenges slide and think about what AI can do, there are clear examples of how AI can provide solutions to almost all of these challenges. And a lot of these are already happening. So everything from suppressing errors, designing better control, decoding errors, developing and enhancing hybrid algorithms, compiling more efficiently, and providing the research community with large language models and copilots trained on quantum computing to help them do their work. It really can tackle or can help tackle almost every important challenge we're seeing in quantum computing today. And so to give one example, this is some work that NVIDIA is doing with a group at the University of Toronto, as well as St. Jude's Hospital. It's called the GPT Quantum Eigensolver. And this is looking at an algorithm called the variational quantum eigensolver. And actually, the group that we're working with invented this algorithm. And so this is a very common algorithm used in quantum computing research today. At a high level, it's a hybrid algorithm where a cost function is minimized by optimizing parameters, which are embedded in a quantum circuit. So it's nice because it's amenable to near-term hardware, but there are several challenges or several issues that are standing in the way of it being useful or providing an advantage. In particular, with regard to trainability for large problem instances. And so the way that this research group, with our help, tried to address this is by taking that classical optimization of the parameters and using a generative model. So the whole circuit structure is embedded in a classical generative model, which is learning the circuits that have desirable properties and generating new ones. So this was run with our software on a supercomputer in Berkeley called Perlmutter. And they found that they were able to get kind of much better convergence to an exact solution for small problems. They're currently working on scaling this up to larger problems. And for details on this, I highly recommend you check out Jin-Sun Kim's talk, which is in about a month. And we'll focus on kind of the latest and greatest with this result and in generative AI for quantum algorithms generally. So that was one example that we worked on, but really this is everywhere now. So these papers are from all across the quantum computing ecosystem in all different fields. So for control of quantum computers, there was a paper from a leading group at Yale using reinforcement learning. Likewise, for calibration and recalibration of quantum devices, a group in Spain is using AI for that. For readout, so looking at kind of analog data coming back from a quantum computer and accurately determining what state your quantum system is in. Machine learning is being used for that. So there's a collaboration between Wisconsin and MIT. And the two results at the bottom are both from the Google group. So one is optimizing quantum circuits using alpha tensor. The other is for error correction, decoding the surface code with a transformer-based neural network. And so not going to get into details. I encourage you to check out all of these papers. They're very exciting. And I also want to point out that all of these have come out in the last 2 years. So there's really been an explosion in the leading groups starting to leverage AI to get past the important blockers in quantum computing, kind of across the board. All right, so how is NVIDIA thinking about this, and how are we supporting this? Our goal is to uh, not compete with anybody in quantum computing. So we're not building a quantum computer ourselves, but to provide the tools that everyone needs to do their work. And there are, in particular, three areas where NVIDIA can really make a unique contribution. The first is simulation. So quantum computers today are small and noisy, and GPU supercomputers are excellent resources for simulating them. And this actually ties into AI for quantum, because one of the big challenges with AI is generating good training data. And that's especially hard with quantum computers. With a good simulator, you can create, you can emulate a quantum computer and generate the training data that your model needs. And so it really fits in nicely with that. The second, which I touched on, is HPC quantum integration. So in order to use quantum computing together with accelerated computing and AI, we need to develop software to make that easy and not painful, much like we did for GPUs with CUDA. And then finally, AI for quantum itself, the areas that I talked about: error correction, calibration, control, development of new algorithms. We can make a contribution here. And below these kind of interest areas is our platform. So I talked about CUDA at the very beginning. To enable all of this, we've created a software platform called CUDA-Q, which is, I'll get into it on a later slide, but it provides the platform to do kind of all of the three things above. Beneath CUDA-Q are libraries for accelerating simulation called cuQuantum, and a system for integration of quantum computing and HPC called DGX-Q. And all of this rests on the same NVIDIA GPU supercomputing platform that's used for AI. So no special different hardware is needed. You can do all this research together with the systems that are doing AI research. And just like our AI platform, all of this is open. So people can use CUDA-Q. You can also use cuQuantum directly. You can also use DGX-Q directly, or build your own solution on top of our GPU supercomputing platform. And so CUDA-Q, this is the most important part of what we build to understand. This is an open source programming model for integrating quantum computing with GPU supercomputing and AI. And the way that it works is it extends Python and C++ with quantum kernels. So anything that you're writing in Python or C++, you can use CUDA-Q to add quantum code to it. CUDA-Q then compiles that code to your quantum computer of choice, be that a simulated quantum computer. So we provide libraries underneath so you can simulate quantum computers on GPUs, or a physical quantum computer. And importantly, CUDA-Q is agnostic to the type of QPU. We partner very broadly. There's already about a half dozen quantum computers integrated with CUDA-Q, and we're always adding more. It's open source, so you can build whatever you like on top of it or with it, or modify it however you see fit. It offers world-class performance, which is critical for the algorithms research that needs to be done, the error correction research that needs to be done, and getting the most out of quantum processors today. And really fundamentally, it enables the easy integration of quantum with accelerated computing. And so if you want to do, things, the things I talked about, like the GPT quantum eigensolver, that was done in CUDA-Q. Using AI for error correction or control is really, really easy through CUDA-Q because it's built for it. So it's a GitHub project. Feel free to check it out. The link is below. And the kind of hardware complement to CUDA-Q is called DGX Quantum. And what DGX Quantum does is, or what it is a GPU system with a low latency link to a quantum control system, which is built by a company called Quantum Machines. And what this means is you can plug in any quantum computer you like to that quantum control system and get access to GPU supercomputing within the coherence time of the quantum computer. So for the first time, you can think about doing AI for quantum error correction before your qubits decay, or doing real-time optimal control or calibration without kind of the bottlenecks of going through the internet or going through a slow connection. And so we see this really as the first step towards tightly coupled um, uh, accelerated computing, quantum computing systems, and really enabling AI for quantum computing today. And just like our AI platform, the way that our quantum platform is built enables us to partner very broadly. And we're really proud to do that. And so just like in AI, we aim to be the only quantum company that works with every other quantum company. And we're proud to say that almost every quantum startup is working with NVIDIA. Almost every group building a QPU is integrating it with CUDA-Q. Almost every quantum framework is accelerated by our libraries, and we count hundreds of quantum partners from the largest companies in the world to academic groups to startups to Fortune 500 companies. And again, we're always expanding this and open to partner. So with this, I'll stop and take questions. But just to wrap it up, the most important points here are that AI supercomputing is critical to the future of quantum computing. And we're already seeing research kind of take off in that direction. And just like we tried to enable accelerated computing and AI in the past, we're now building a platform to enable groups to solve the important problems in quantum computing.